So we somewhat did this already, but I'm going to redo this because we now have another tool at our disposal, the Lagrangian. And by transforming the Lagrangian itself, we can explicitly say, okay, this is gone away, we can now do this, and so on and so forth. And we can approach this problem in a more modern basis. So I have these two masses, M1 and M2, and they, of course, have some positions, let's say R1. And let's see if I can hit this here. R2. So there's some line connecting these. I can draw a vector. Try to be more colorful. So R vector. That is, in this case, it's going to be R2 minus R1. R1, and there's going to be some center of mass over here. Say R, with R is the position of the center of mass, and what we are going to do is, you probably know this already, I don't need to justify this definition. Okay, so this small r1, small r2, and capital R, they're all given in the inertial frame. Right? We are going to take this motion and divide this into the motion of the center of mass and the motion about the center of mass. Right? So we are going to define the positions with respect to the center of mass. And in some cases, this is not going to be an inertial frame if there is an external force, but we are going to neglect external forces, so that's going to be inertial as well. Now, when we're looking at the relative motion, this R, one thing to keep in mind is that this is not an inertial reference frame. Right? In general, this M2, this M1 is going to be accelerating. So if I fix it at the origin, if I measure my position with respect to this M1, I'm no longer in inertial reference frame. I'm going to have some additional forces. But this is not a big problem. We can always go back to our inertial frame by some simple algebra. We can make all the calculations for the relative motion and then come back. And so first, let's define our R1 prime and R2 prime. So let's call this R2 prime and this one R1 prime. So these are the, let's see, what is this? This is R1 minus R. These are the positions with respect to the center of mass. So this is going to be minus M2 by M1 plus M2 R, and this is going to be M1 over M1 plus M2 R. Let's see if this makes sense. So first of all, R2 prime is going to be in the direction of R, and R1 prime is opposite to R. That checks out. Now, if M1 is larger, then this R1 is going to be a smaller vector. The center of mass is going to be closer to M1, and that checks out as well. If M1 is larger, this magnitude is going to be larger than this one. So I think this makes sense. Yeah? I don't know if I gave out the algebra correct or anything like that, but at least simple checks to give a sensible answer. Now, what I'm going to do is I'm going to write my Lagrangian, and my Lagrangian is, of course, T minus U, and T is just a function of velocities, R1 dot and R2 dot. My U is going to be a function of R1 minus R2, and it's possibly its derivatives, and so on and so forth. Okay? So I'm going to neglect the external forces. I'm going to just get the interaction forces between these two particles, and that means that my potential or my potential energy can only depend on the separation and the relative velocities, and so on and so forth. It cannot depend on anything else. It cannot depend on how I choose the origin. Right? So it cannot depend on the absolute values of this, but only to their differences. Now, let me erase this because I will do some algebraic manipulations. I don't need the figure. E, the kinetic energy is going to be a half M1 R1 dot square plus a half M2 R2 dot square. And I can take this. So if this is correct, then R1 is R1 prime plus R, and R2 is R2 prime plus R. I take the derivative of that and square that over here. What I'm going to get is a half M1 R dot square plus a half M1 R1 prime dot square. But this is getting a little bit complicated. I will just reread them for you. I'll put symbols here. This is simple. This is a half M1 capital R dot squared. This is a half M1 R1 prime dot squared. Okay. So it's the velocity of the mass 1 about the center of mass squared. And this is for the second mass. Now I can add these up. This is going to be a half M1 plus M2 R dot square plus a half. What do I get here? M1 times M2 over M1 plus M2 R dot square. That R, remember, is R2 minus R1. But it's of course also R2 prime minus R1 prime. Means the relative position everywhere. This is R dot square. And our potential energy is going to be just R dot, etc. And by looking at this, without doing any computation, one thing you can say is that this capital R, which is a perfectly well generalized coordinate, is cyclic. Right? Now Lagrangian depends on our capital R dot, but it doesn't depend on capital R. What does this mean? Its conjugate momentum is conserved. Right? That will be the conjugate momentum of this would be the linear momentum of the center of mass. In the absence of external forces, which is what is bringing this, okay? In the absence of external forces, the linear momentum of the center of mass is going to be conserved. I can do this, I can say this without doing any computation at all, which means I can just take this up. Right? I can take the R, so R is cyclic. So it can be ignored. In fact, another name for cyclic coordinates is ignorable coordinates. And the conjugate momentum for R, this way, is going to be m times so this is conserved. Any questions? Now I can solve everything in terms of the relative coordinates and the center of mass coordinate. And then I can go back. Okay? If I know those, I can always recover my, because I have these two equations, and presumably I also know the masses, I can always recover my original inertial coordinates. So even though this is not the coordinate is measured in inertial reference frame, there is no problem from physics point of view. Any questions? Okay. Now, to proceed further, we are going to assume, some form of this. And we are going to turn this into central force. Okay, so I assume two things simultaneously. I said it only depends on the magnitude of the relative position, and it doesn't depend on the higher powers. So it's going to be a conservative force then. Okay, we have a very simple relationship for the potential energy, for which we can take the derivative, and it's going to lead to some force. So we have a conservative central force. I call this a central force because if the potential energy is given this form, then the force has only a radial component. It should be pointing towards some force center. And because it doesn't depend on the direction and just the magnitude, our problem is spherically symmetric. The one-body problem, and we have a single body, just having this position vector of r, what we define as the relative motion vector, and it is seeing the potential that's spherically symmetric. So the problem is completely spherically symmetric. And if there are multiple particles going around the spherical symmetric potential, you could say the potential is symmetric, but perhaps the solutions are not going to be. But in this case, that there is no way around this. I don't need to show anything more. Now, yeah.
Do we say spherically symmetric because the potential is independent of the angles?
Yes. It only depends on the magnitude. So the potential is spherically symmetric. No matter what I choose for theta and phi. So it could depend on your distance from the force center. It should. Otherwise, there is no force. But apart from that, it's spherically symmetric. Now, if the problem is spherically symmetric, every component of angular momentum has to be conserved. So if a problem is spherically symmetric, it means that it's symmetric around there's rotational symmetry around every axis. And we showed that if there is rotational symmetry around an axis, then the angular momentum along that axis is conserved. Now, this for a spherically symmetric system happens for every axis in the system. So every component of angular momentum is conserved, but this means that angular momentum is conserved. Right? Saying every component of angular momentum is kind of superfluous. So therefore, angular momentum is conserved with no qualifications. Not a component of angular momentum. All components are conserved. It is conserved. And we write our angular momentum like so. So there are lots of different symbols used for a lot of different, like for this angular momentum, you can see 3-4 different symbols. I'm going to try to stick to the book symbols. I'll let you know when I deviate. Okay. Now, this is a conserved vector, and L is perpendicular to R. Okay. Now, what does this tell you? So you have a conserved vector in space, and your position vector is always perpendicular to this vector. Right? So it must lie in a plane that's perpendicular to this vector. Right? Your motion is restricted to a plane. Conservation of angular momentum implies that you have an orbital plane and you always move in this. Okay? So because of this, motion is a plane. Okay? Perpendicular to L. If L was not conserved, this was just moving around, just because you're perpendicular to this would not mean that you're actually moving in a plane. However, we don't actually require this to be conserved exactly. We only need its direction to be conserved. That's something you notice. Its magnitude can change. You will still be in a plane. So as you're moving in a plane, that doesn't imply angular momentum is conserved. Okay? Your angular momentum could be not conserved, and you could still be moving in a plane. So the converse of this is not true, not strictly. Moving in a plane implies the direction of angular momentum is conserved. But of course, when angular momentum is conserved, its direction is automatically conserved. So You don't say anything more. Okay. Now transform to this. Plane and use polar coordinates r and theta with origin at the force center. Okay. Now, our Lagrangian, just t minus u, is going to be, well, let's first write this a bit more explicitly, because we are going to need those formulas. So my r, the position vector, is just going to be r head. Right? This r head is the unit vector in the radial direction. My velocity vector is going to be r dot r head plus r theta dot theta head. Now, this is not obvious. This is not obvious because this is something that you don't see in Cartesian coordinates. Right? So if you write something like your r is x head and your v is just vx x head. There's nothing more. It doesn't happen in polar coordinates. In polar coordinates, you pick up another component. And this is not something you haven't seen before. This is the radial component of velocity. And this is the transverse component of velocity, sometimes referred as the theta component of velocity. Okay? That t is not tangential, it's transverse. Keep it in mind. So radial velocity. This is transverse velocity. But where did this come from? And this is something, this is really motion in r. And this is r times theta dot, something you have seen before, maybe even in freshman year. But how would you drive this?
Isn't it the change of the r hat?
Right. So r hat is not a constant vector. So this doesn't happen in Cartesian coordinates, because in Cartesian coordinates your basis vectors are constant. Here your basis vectors, r hat and theta hat, are not constant vectors. So this comes from, this is in fact proportional to r hat dot. You could write this, this is r hat dot. But it's looking very funny, so I'm not gonna do that. How would you drive it though? So that is 80% of the way you're there. But if you want to get this expression,
we should express the polar vectors in the Cartesian form, and then we will have the sine and cosines, and we can derive this.
Very good. So you can write this, for any position over here, your r is going to look like this, r hat, and there's going to be some theta associated. You can divide this into components, x hat and y hat, and x hat and y hat are constants, so you can just take its derivative, but they're going to be preceded by sine theta, cosine theta factors, and those are going to bring this thetas. Okay? All right, excellent. So this is going to be still your homework, though, right? Just so the people who are not here can also decide. All right. So now we can write our Lagrangian, these expressions. I'm just going to, put this down. It's not too hard to make a rigorous derivation of this, but we don't need it. Half m. So this is going to be r dot square plus r square theta dot square. This is the kinetic energy part minus c of r. And now I hope it becomes clear why we switch to polar coordinates, because.
May I ask something?
Yeah, go ahead.
So we have the r dot in the above expression, and then while expressing the kinetic energy, we didn't take the square of the full expression, but the individual terms. So is it like,
Because their dot product is 0, they are still perpendicular. to each
okay,
other.
so okay.
They are not constant vectors, but they move like this.
Okay,
So
so
as
they
you go
are
from
still orthogonal. Okay.
there, yeah, they're still orthogonal. Okay, but yeah, so it should now hopefully be clear that why we switch the polar coordinates. When you look at this, theta is cyclic. Theta that appears in the expression, theta itself doesn't. So theta is cyclic, which means the conjugate momentum for theta is conserved. And you can calculate the conjugate momentum by taking the partial derivative of this with respect to theta dot, and that's going to give you m r squared theta. This m r squared, sorry, theta dot. Okay. And this is, we're going to call this just L, small l, that's what the book is doing. I would call this capital L, I don't know why they're switching to small, but this is the magnitude of angular momentum. And so we can integrate this variable out as well. And one of our first equation of motion, let's say, is this m r squared theta dot is L. And we're just going to integrate this to get some expression for theta. Now, this is a nice geometric interpretation. I don't think I can fit this here, so I'm going to erase this one. So this is conservation of angular momentum. And as you probably heard before, conservation of angular momentum has something to do with one of the Kepler's laws. Right? So Kepler laws are, there are a number of them, but one of them is about the area swept by the planets in a given amount of time. Right? So the planets are on elliptical orbits, so they move at different rates when they're closer to the sun or farther from the sun. As they come closer to the sun, they move faster. So it seems like something that there is no constant, but there is a constant. The area swept in per unit time is a constant. Right? So as they come closer, the area swept is going to be smaller. So let's keep it going here. Let's say that our orbit is like this, and I go from here to here. So the area swept, I'm referring to this. Okay. So as they come closer to sun, they move faster. So the arc length gets bigger, but the radial distance, which also determines the area of this, gets smaller. When they're farther, they move slower. So per unit time, they trace a smaller arc length, but now the distance is farther. So, and this exactly compensates each other. Right? So how do we get this? Well, we're going to, let's call this our R. Okay. And I move over some distance d theta over some little time dt. Okay. And dA dt, d theta by dt is given here. So this one is going to be r d theta. Okay. Because it's an infinitesimal angle, I can always say that the arc and the chord are the same. So this is strictly speaking the arc length. I just drew a chord there, it doesn't matter. And the area over here is going to be the base of this triangle times its height divided by 2. So r d theta times r over 2. This is a half r squared d theta. Okay. Now, as this becomes infinitesimal, the area I'm neglecting here, I'm taking this one out and I'm completely neglecting this, and that approximation becomes better and better. I'm not going to show it, but you can show that the area of that is second order in your differentials. Right? So not only it's this one, the differential, this one is also a differential. That's the idea. So the area I'm neglecting is second order. So if I really go to the limit, it just disappears. I only keep in the limit, I only keep the first order differentials. All right, now you can take this and rewrite this. dA by dt is going to be a half r squared d theta by dt. But I know what this is. It's just something to do with the area. So this is going to be L by M, the specific increment divided by 2. So the rate of surface area is a constant. Okay. Now I switch to just using M. So this M is now what used to be my reduced mass. I could keep using mu, but the book switched to M, so I'm switching to M as well. Right. This M, that M, they're all my reduced mass. And I'm talking about the relative motion. But the relative motion is has this property. And if you first figure out the properties of the relative motion and then go to the motion about the center of mass, you'll find that when the relative motion is an ellipse, the motion about the center of mass is also an ellipse. So this is something again peculiar to the Kepler problem, but it's going to work in our case. Right. So even though we are showing this for the relative motion and not for actually no, this directly applies to the motion of the planets about the sun. It is relative motion, so I don't need to justify this. Right. But this from this it follows. Kepler's third law, is it the third law or this? No, this is the second law. The first one is their ellipses. The second one is they sweep equal areas, and then the third one is ratio of the r cubed by t squared is constant. So this is the Kepler's second law. Okay. Now we have this one equation for theta. Now the equation for r. So we can also, of course, write an equation. This looks like this. So d by dt r minus r theta dot square plus del v by del r is 0. And so in general, we're just going to call this some minus central force. Yeah. So this is just one of the Lagrange equations. So this is Lagrange equation for the r coordinate, and we can simplify this obviously. R double dot minus r theta dot square is equal to f of r. So this is one way to look at this. We can go ahead and turn this into something that depends on r only by exploiting this fact. Okay, so we can take this equation and substitute this here. You basically take the expression for theta dot and put it in this equation, and we're going to get r double dot minus del square by r cube is equal to f of r. Okay. And so this is the second equation that you need to solve. Now, there is another integral of motion. So this is one of the first integrals, this integral of the motion. There's another integral of motion. What is that for this problem? When your potential is just given by r. It's energy. Right. The energy is going to be also a first integral. And let's write that down. And the equation for energy R squared it's nothing minus, right? Plus, no, plus. Okay, so there are, we can just say that, okay, this is the energy, it's T plus V. I can just write this, or you could derive this by algebraic methods explicitly to show that this quantity is actually conserved. You can take this quantity, take its derivative, show that it's going to be conserved, and so on. It doesn't really matter. But these two first integrals are going to allow you to integrate the problem completely, or at least formally. Right? We still did not specify what is potential and what the central force is, so you can't go too far with this. But formally, what you can do is that you can get an expression, something like dt is dr divided by something square root stuff, and then you can integrate this, okay, both sides, and you can say that t minus t0 is going to be dr of this blah 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 blah, and then you can invert this and get r the function of time, and then we can take this by using the relationship, especially this one, right, by saying that dy d theta is something dt involving r. You take this expression, put it in the expression over there. So this one involves r, as you see. You can also integrate that one and obtain an expression, right, for the theta. Now, I did say something very quickly here. I said that you take this expression and invert it to get this. How do you invert this? This is a horrendous integral. First of all, how do you take the integral? If I give you some VR, you can't always take it, right? For the most interesting one over R potential, you can. Everything else, pretty much you can't. So Shai, how would you take this integral? You're nodding your head.
So probably it's going to be, if we consider the gravitational potential, it's going to be, the integral will be logarithm, and the inverse means the exponential of.
No, but this is going to be something like the square root, and the VR is going to be somewhere in that square root. It's not going to be just the logarithm. So it's something complicated. But then for the 1 over R potential, it can actually be taken. Integral can be taken.
So I can use probably the change of variables. If it is square root,
not 1 over R, if it's something very complicated, what we should do?
So, for example, if it is square root something squared minus some or plus something squared, then I can use trig change of variables like tangent and
trigonometric substitution.
Exactly, substitution. And then that trick would allow me to take this integral.
Sometimes.
Yeah,
if it's simple enough.
Okay.
But if that doesn't work, what would you do?
Numerically, maybe?
Yeah, you do it numerically. This is the answer I'm looking for. So almost all the problems you're going to see here is going to be solved numerically. Okay? You can't go very far with analytically. And you need to know, if you want to solve these problems, you need to know how to do this numerically. Same deal here. Yeah. So you get an equation here. You get your t as a function of r, which is okay, sounds useful, but usually you want r as a function of t. What do you do? How do you invert this numerically? There is almost always no other way. Even if you can take this step analytically, the function you're going to get is something horrendous looking, transcendental, unless it's harmonic oscillator or Kepler problem, the two problems that you can actually solve. You're going to get something you can't invert by hand, so you do this numerically. And the numerical inversion is Newton-Raphson method, something like second method, bisection, whatever. But you need to learn this. Okay? You need to learn how to do this numerically.